Okay, so to pick up where we left off in the last part, chemical formulas or formulae, if you prefer. For compounds, what we do is we take the symbols for the elements involved in the compound and we combine them with each other, basically one right after the other, to show what elements are present. And we also have a way of showing how many atoms of a given element are present in each unit of the compound. There are different ways of writing chemical formulas, and they will convey different information. The molecular formula just shows what's present in each molecule of a compound, how many atoms of which elements. And the element symbol itself represents one atom of an element. If there's more than one atom of that element present, then what you do is you use a subscript number after the symbol of the element, showing how many of them there are. But that subscript is important to remember, and I squeezed it in there. The subscript only applies to the symbol immediately before it. So like in H2O, that means that each molecule or each unit of H2O consists of 2 atoms of hydrogen and 1 atom of oxygen. You can write it like this. You could write it like this. This way is more of a structural formula, which we'll get to down below here. It shows you how the atoms are arranged. And the fact that it's bent, why is that? We'll get to that later. So don't worry about that right now. I just didn't want to draw it wrong. So anyway, H2O has 2 atoms of hydrogen in it. That 2 only applies to the H, the symbol right before it, and 1 atom of oxygen in each molecule of the compound. If you want to convey that there are 2 atoms of hydrogen and 2 atoms of oxygen in each molecule of the compound, then you would write it like we write the formula for hydrogen peroxide, H2O2. And each molecule of hydrogen peroxide would look something like this: 2 hydrogens and 2 oxygens. And again, the fact that it's bent like this and that the oxygens are in the middle, we'll get to that later, so don't worry about not understanding why that is. But this is just to show how many oxygens and how many hydrogens there are. If there's 1 atom of each element, then you would write it like we write the formula for carbon monoxide: 1 carbon and 1 oxygen. Or you could write it like if there are 2 oxygens and 1 carbon, then you would write it like we write the formula for carbon dioxide, CO2. The 2, remember, applies only to the oxygen, not to the carbon. So there's 1 carbon and 2 oxygens, or a structural formula would look something like this. The fact that there are double lines here, which stands for something known as a double bond, we'll get to that later. Don't worry about that. I'm just showing that there's 1 carbon and 2 oxygens in each molecule. Okay, so each molecular formula represents 1 molecule of the compound, or it can be used to represent the compound in general. If you're writing, say, H2O as part of a chemical reaction, then it would generally be understood to represent 1 molecule of water. But if you write H2O on a jar of water, then that would be, represent the element or the compound as a whole. We also have structural formulas, as I just mentioned. That's what I was drawing here. Structural formulas uses the symbols for the elements, and it arranges them in a way that gives you some clue as to how they are really arranged in the actual molecule. So for water, we would draw it like this with the oxygen in the middle. The lines are bonds. So the line between the oxygen and the hydrogen represents a bond, and the other line between the oxygen and the other hydrogen also represents a bond. And so that's what H2O would look like. CO2, we already saw. The double line represents a double bond. And what that means, we'll worry about that later. But anyway, carbon is in the center and the oxygens are in either side of it. And the molecule really is arranged in a straight line like it's drawn here in the structural formula. Just like the water molecule really is bent like this. For methane or CH4, the carbon goes in the middle and the hydrogens are around the outside. And there are a couple different ways you can draw this, because some molecules really are flat and can be represented accurately in 2 dimensions, like water and carbon dioxide. But some molecules, like methane, are actually 3-dimensional and cannot easily be represented accurately in 3 dimensions. So drawing it like this does accurately convey that carbon is in the middle and it is bonded to each of the hydrogens separately. But it doesn't really show you what the compound really looks like. This makes it look like the molecule is flat and kind of T-shaped, but it's not. Actually, a molecule of methane looks like this. And this is known as a tetrahedron. We'll get to the specifics of this later, but for right now, I just wanted to show that there is another way of drawing some compounds that for some of the more complicated compounds, you might have to draw it differently from this way if you want to show what the compound really looks like. The best way you can draw this on flat paper is something like this, which corresponds kind of to what I have here, where the straight line represents something that would be flat against the paper. The wedge represents something that's coming out of the paper like this. And then the dotted wedge represents something that's going back into the paper like this. And so the black is the carbon, the whites are the hydrogens, and this is what it looks like in 3 dimensions, represented by that. That's known as a ball and stick model, and it's also 3-dimensional, whereas this is 2-dimensional, and so it's not completely accurate. Structural formulas can be used for molecular elements, that is, elements that tend to exist as molecules rather than separate atoms. So hydrogen is a diatomic element. You can just write it as H-H, where the dash represents a bond. Oxygen is also a diatomic element, only actually in the case of oxygen, the oxygen atoms are connected by a double bond, so we'd write a double line. And again, don't worry about double bonds just yet, but I didn't want to draw it wrong. Nitrogen is attached to another nitrogen by a triple bond. So that's why we drew 3 lines here. And again, we'll get to those later, so don't worry if you don't know what a triple bond is. Sulfur is often found in the form of rings involving 8 sulfur atoms, which you often write as S8, and you could draw it as a structural formula like this. Notice that's an octagon with 8 sulfurs, 1 at each corner of the octagon. We should note also the difference between a subscript number and a coefficient. Subscript number is a little number that comes right after the symbol for an element, like in H2. That represents 2 hydrogens that are bonded to each other. So subscripts represents how many atoms there are connected to each other. Like in this case, H2, that's 2 atoms of hydrogen connected to each other through a bond. Whereas a coefficient is a full-size number that comes in front of the symbol for the element. And that represents how many separate atoms of the element you have. So H2 means H bonded to H. 2H means an H over here and a separate H over there. So a coefficient means that's how many you have and they're separate from each other. And that's an important distinction, especially once we get into writing chemical reactions. If you combine a coefficient and a subscript, like you write 2H2, then that means you have 2 separate groups of 2 hydrogen atoms attached to each other. So 2H2 means H-H over here and H-H over there. And to get the total number of hydrogen atoms, all you have to do is multiply the coefficient times the subscript. 2 times 2 is 4, and look, we've got 1, 2, 3, 4 hydrogen atoms. And that will also be important to remember as we get into writing chemical equations later on. There is also the empirical formula. The word empirical literally means experimental, and it's called this because this is often the chemical formula that you get from chemical analysis or experiments. When you take a compound and you do a chemical analysis on it, it often gives you the lowest whole number ratio of one element to another in the compound. and it doesn't necessarily tell you exactly what's present in each molecule. So an empirical formula is the lowest whole number ratio of the elements to each other in a compound. So you can go from a molecular formula to an empirical formula really easily. All you do is you take the molecular formula, you look at the subscripts for the various elements present in each molecule of that element, and if they have any common factors, you divide by the largest common factor between them, and you write the result. Some compounds, in fact, a lot of compounds, end up having the same empirical formula as they have molecular formula. Like, for instance, H2O. When we write H2O, it's kind of understood that the subscript for the oxygen is 1. So the subscripts are 2 and 1. There's no common factor there besides 1. And if you divide by 1, the numbers stay the same. So the empirical formula for H2O is H2O. That's the simplest ratio you can get. On the other hand, if you have hydrogen peroxide, it's the formula, molecular formula is H2O2. Those are both obviously divisible by 2. So do that and you get HO. That is the empirical formula for hydrogen peroxide. If you take glucose, or actually that's the formula for any number of different sugars, but glucose is probably the best known, which has a formula of C6H12O6, you'll notice all of these numbers are divisible by 2, but they're also divisible by 3, and they're also divisible by 6. So you divide by the largest common factor, and you get CH2O. And that would be the empirical formula for glucose. And that's how sugars came to be called carbohydrates too, because the empirical formula is carbon followed by water, and water in Greek is hydro, so carbohydrate. And also when you combine acids with sugars, you tend to get a lump of carbon and steam being given off, in other words, water. So again, carbohydrate. For ionic compounds, we always use the empirical formula. For compounds like water, hydrogen peroxide, and glucose, we use, they exist as separate independent molecules, each of which has this many atoms of each element in them. And so we use the formula for each independent unit of the compounds. But there are some compounds that are known as ionic compounds, and that they consist of a metal and a non-metal. The book uses the example of titanium dioxide. Titanium is right here in the periodic table, and this is the part of the periodic table with metals in it. And oxygen is way over here, and this is the part of the table with non-metals in it. So titanium dioxide contains a metal and a non-metal. So therefore, it's an ionic compound. I'm using the example of sodium and sodium chloride, salt, in other words, because it's easier to draw than the structure of titanium dioxide. You can look at the book if you want the TiO2 structure. Sodium is way over here on the left. That's where the metals are. Chlorine is way over here on the right. That's where the non-metals are. So again, metal, non-metal means ionic type compound. And the problem with them is that they exist as sort of a continuous three-dimensional array of alternating positive and negative ions. And it goes on and on and on in 3 dimensions. They don't exist as separate little units called molecules. They exist as big networks of positive and negative ions. And I've drawn a little piece of a sodium chloride network here on the page. And this is just a small little chunk of sodium chloride, and it actually goes on in 3 dimensions. So it not only goes on this way and this way, but it goes on this way as well. This is still much simplified because, for one thing, sodium and chloride ions are not equal sizes. But anyway, you can see from this that the way it alternates, if you count up just from this little segment or this little chunk of sodium chloride, you have a total of 12 sodiums, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you have a total of 12 chlorines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So for this chunk of sodium chloride, our formula would be Na12Cl12. But those subscripts would change depending on how big a chunk of salt you have. For any significant chunk of salt, even a single grain of salt, the subscripts would actually be billions and billions. You'd have billions and billions of sodium ions and billions of chloride ions. And so, you know, who knows what number to write? Are you going to sit there and count them or what? But the fact, what we do is we simplify that by taking the fact that whatever the number of sodium ions is, whether it's 12 like it was here, or whether it's billions and billions like it would be in a grain of salt, the number of chloride ions is going to be the same. So we divide by whatever that number is. We don't even have to know exactly what the number is. We know it's going to be the same number as for the sodium ions. And we divide by that number and we get NaCl, because it's always a 1-to-1 ratio. And so we use the formula for NaCl, even though you can never actually have, or not very likely that you would ever have, one sodium ion and one chloride ion together and not attached to anything else. And if you did, it would be much too small for you to see or deal with. If you have a bunch of different combinations of one sodium and one chlorine attached to each other and not to anything else, and you put them together at the same time, they will start attaching to each other and you'll get a three-dimensional network like this. So anyway, that's why we always use the empirical formula for ionic type compounds. Okay, we can find the molecular formula from the empirical formula, and the book kind of glances up against this, but it doesn't actually show you how to do it. So I figured we might as well do it now and get it out of the way. So you can actually find the molecular formula of a compound if you know the empirical formula and the molecular mass of the compound. That is the mass of each molecule of the actual compound. And probably the best way to show you how to do that would be to show an actual example. If we have a compound with an empirical formula of CH2O, and we know that each molecule of the compound has a mass of 120 atomic mass units, or 180 atomic mass units per molecule, what is the molecular formula? Well, we've got the empirical formula, and we've got the mass of an actual molecule of the compound. We know that whatever the formula for the molecule is, it's going to be some whole number multiple of the empirical formula. And the way that you find out what that whole number is first of all, you have to find the mass of the empirical formula. The empirical formula here is given as CH2O. That means each molecule of this formula would have the mass of 1 carbon plus 2 hydrogens plus 1 oxygen. So if you go to the periodic table, we see the mass of carbon is 12. It's 12.01, but for most purposes, rounding it off to the nearest whole number is close enough. So we'll call the mass of carbon 12. And each hydrogen has a mass of 1.008, but again, it's okay to round it off to 1. But there are 2 of them, so you have to multiply that by 2. And then we see oxygen has a mass of 16, and in this case, it really is exactly 16. So you add 12 plus 2 plus 16 together, and you get 30. Okay. So each unit of the empirical formula has a mass of 30 atomic mass units per molecule. Then what you do to find out how much, basically how many multiples of the empirical formula you have to have for the molecule, you just take the mass of the molecule over the mass of the empirical formula, and you get a result. In this case, 180 divided by 30 is 6. If the result is not a whole number, then you can round it off to the nearest whole number. If you're using actual experimental data, you get might get something like 5.97 instead of 6. So round it off to 6. And then what you do is you take that 6 and multiply all of the subscripts in the empirical formula by that number. So the empirical formula was C, it's understood to be C1, H2O1. And so the actual molecular formula would be C1 times 6, H2 times 6, O1 times 6, or in other words, C6H12O6. So that is the molecular formula, again, for glucose. And actually, it's also the molecular formula for several different sugars. So coming up with the molecular formula like this doesn't necessarily tell you exactly what compound it is, but it does help narrow it down quite a lot. So C6H12O6 is the molecular formula for glucose, but it's also the molecular formula for several other sugar type compounds. And the difference between them is they've got the same number of atoms of the same elements, but they're arranged differently. And therefore they have somewhat different physical properties, although their chemical properties are the same. And when you have two compounds that have the same number of atoms of the same elements in them, but they're arranged differently in space, that's known as isomers. So say glucose and one of the other sugars that has the same formula, they would be isomers of each other. Okay. Section 2.5 is on the periodic table. And we've seen some of the periodic table and we've discussed it some before also, but this is where we'll kind of bring together everything we've said and some other stuff too. It was found back around 1870 by a couple of different scientists, Mendeleev and Meyer, but Mendeleev went further with the idea, so he usually gets the credit today, although Meyer was working on the same kind of thing also. They found that if you take the elements in the periodic table and arrange them in order of increasing atomic mass, what you get is sort of a periodic trend in properties. In other words, the properties will change in an orderly, predictable way, and then they start repeating at a certain point, and they will change again in an orderly, predictable way, and then they come back to the beginning and they start changing again over and over again. Mendeleev and Meyer in 1870 didn't know about atomic number, that is, they didn't know about protons yet, so they arranged their periodic tables according to increasing atomic mass, which was known then. And they found that when they did that, there were a couple spots where the properties didn't quite vary as expected. Lo and behold, though, once protons were discovered and the periodic table was rearranged according to atomic number, almost all of it was the same as the order Mendeleev and Meyer had, but there were a couple spaces where elements switched places. And that had the effect of restoring the trend. So if the elements are ordered according to atomic number, the trend is much better and you get a very predictable variation in properties as you go across the periodic table. Just as a quick example, over here on the left, you've got very, very reactive metals. So if you go from left to right, you've got very reactive metals, less reactive metals, and then nonmetals. And then you come back to this line, you've got very reactive metals, less reactive metals, nonmetals. And it goes like that over and over and over again throughout the periodic table. And Mendeleev and Meyer were the first ones who really noticed that and who did anything with it. And the real value to what they did was that they were able to use the trends in the periodic table to predict the discovery of elements that hadn't been discovered yet. You know, 150 years ago in 1870, they didn't know about all of the elements we know about today. A lot of them had not been discovered yet. So there were actually gaps in the periodic table, you know, where there were gaps in the masses of the known elements. Mendeleev left a gap in the periodic table. And because of the way the properties change in a predictable way, when you go left to right across the periodic table, he was able to predict that someday elements would be discovered to fill in those gaps. And he was able to predict very accurately what the properties of those elements would be, just based on the properties of the elements that came before and after them. And as I said at the beginning of the semester, the mark of a really good scientific theory is the ability to predict future results in experiments that haven't even been done yet. And the fact that Mendeleev's periodic table was able to predict not only the existence, but the properties of these elements that hadn't been discovered yet, that shows that he was definitely onto something. And so today we order it by atomic number, which makes the trends even better. And the periodic law is what I was talking about, the fact that the properties repeat over and over again in a predictable repeating way. And that's known as the periodic law. The periodic table, of course, is where we compile the information on the chemical elements. When Mendeleev listed out the elements according to increasing atomic mass, he got basically a list of elements and he listed out their properties. And he noticed that the properties tend to repeat at certain intervals. And so what he did was he stacked the elements up with elements that had similar properties vertically on top of one another in what came to be known as groups or columns. And so the elements in this first column here have a lot of properties that are very, very similar or even exactly the same as each other. And all of the elements in this second column have properties that are very similar or even the same as each other, and so on throughout the periodic table. And that's why it looks the way it is. Actually, the way it looks the way it is because of the way the electrons arrange themselves when you have different numbers of electrons, but we'll get to that in the future. But anyway, you have the vertical groups contain elements that have properties that are very similar, or in some cases even the same. So the groups are where he took the elements with similar properties and put them into vertical columns. There are 18 groups in the periodic table. The older numbering system divides them into A groups, which are called the main groups or the taller groups, and B groups, which are the shorter groups in the middle, also known as the transition elements. So you have 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. And then the B groups are these low-lying groups in the middle. Or the newer numbering system is just numbers 1 through 18. So you get 1, 2, 3, 4, 5, 6, blah, 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 13, 14, 15, 18. I prefer the A and B system, but the trend is actually definitely towards the 1 through 18 system. The elements, since they're listed in order of atomic number or and more or less by atomic mass, that means the elements on top are lighter than the elements at the bottom. So elements get heavier as you go down a group, and they also get heavier as you go left to right, with I think 2 exceptions here and there in the periodic table where you actually go from heavier to lighter as you go from one space to the next. Each element has a space of its own containing the symbol for the element, the atomic number, which is the whole number in each space, and also the atomic mass, which is the weighted average of all the masses of the isotopes. And that's the number with the decimal spaces in it. A lot of periodic tables contain other information too, like for instance, the name of the element. It might give you a key as to the state of the element at room temperature and room pressure. That is solid, liquid, or gas. This periodic table here really doesn't, but some do. They might also give you a clue as to whether it's a metal, a non-metal, or a metalloid. This periodic table does. It was originally in color though, and the black and white copy makes it hard to tell the difference between metals and metalloids, or semiconductors, as they're sometimes called. Sometimes they'll also give density and sometimes other information depending on what the purpose of the periodic table is. The horizontal rows, the numbered rows going across the periodic table, are known as periods because across the periods, the properties of the elements vary periodically. They're sometimes also known as series. Like I said, the properties of the elements vary predictably across a period. But then you come back to the next period down and you start over again. So you have very active metals, less reactive metals, and then nonmetals. And then you come back down to the next period, very reactive metals, less reactive metals, nonmetals, and over and over and over. And actually, those are just very sort of crude ways of describing the properties. Exact properties, like exactly how reactive they are, or things like, say, densities or the types of compounds they form, they will also vary a little bit from one space to another as you go across the periodic table. And you can track the detailed variation in those properties as you go across. And that's how Mendeleev was able to predict the discovery of certain elements and what their properties would be, because he looked at the elements on either side. I believe germanium was one of the ones he predicted, and see, okay, gallium has these properties, arsenic has these properties, germanium will be somewhere between those properties. The chemical properties tend to be similar going down a group, so he was able to look at silicon and tin, which were both known in his day, and say, okay, silicon and tin form these types of compounds with these types of ratios with other elements. So this element that's yet to be discovered will also form compounds with those types of ratios with those other elements. And he was right about that. Okay, so the lanthanide and actinide series, these two sort of outcast rows of elements down at the bottom of the periodic table, they actually belong in this space here. Notice how the numbers jump from 57 to 72 from lanthanum to hafnium. That's because all of these elements here are squeezed in there. And this number jumps from 89 to 104 because all of these elements are squeezed in there. The reason they take these two rows down below is because if you stuck them in there, the periodic table would be so wide that it wouldn't fit on one page. Or if you reduced it enough to fit on one page, it would be so small you couldn't read it. So for convenience, they just took these down here. If you Google periodic table on the internet, you can actually find versions of the periodic table that have these rows in where they belong. And yeah, it is really wide. So that's why they did that. I see we are probably at the end of this video now, so I'm going to have to cut it off there, and that'll be that will be it for today.